Everyone, in this video walkthrough, we'll be going over a star algorithm. We'll be talking about the problem a star is trying to solve. We'll be talking about some intuition behind what a possible solution could be. Then we'll talk about that solution, and then, yeah, we'll kind of wrap up from there. All right, so the problem that a star algorithm is trying to solve is that we want to find the shortest path from some start vertex to some goal vertex. Okay, so first thing to notice here is like, why is this different than Dijkstra's? Well, if we kind of recall, in Dijkstra's algorithm, the problem is that we want to find the shortest path from a start vertex to all other vertices in the graph, while in A star, we only care about finding the shortest path from a start vertex to a given goal vertex. All right, so let's kind of say that we maybe have, I think it's very helpful to think about A star algorithm from the point of view of a US map, okay? So let's say that we have like the US map. I'm going to draw it slightly poorly because I'm not that good at drawing. So we have, there we go, the US map right here. And let's say that we're trying to get from, let's say that this is Chicago. Let's say we're trying to get from Chicago to LA. All right. So let me just drop in a couple other random places here. Let's say like this is like Denver. And let's say like this is New York. All right. So if we're trying to find the shortest path from Chicago to LA, you might say, hey, Soham, let's just run Dijkstra's algorithm, because Dijkstra's algorithm will eventually find the shortest path from Chicago to LA. Well, the problem with Dijkstra's algorithm is that it's not really meant to solve that problem, right? So what's going to happen is that we're going to visit a lot of vertices we don't really need to visit, because what Dijkstra's algorithm does is that it keeps visiting the next closest vertex, right? So what you can kind of think about is that when we're searching with Dijkstra's algorithm, the search kind of looks something like this. We kind of keep searching all of the vertices in a circle space around Chicago, right? So this is kind of what's happening in Dijkstra's, is that our search is kind of starting from Chicago and growing outward. So what this means is that we're probably going to end up visiting New York before we visit, say, Denver, right? Notice that we're going to visit New York before we visit some place like Denver, right? And this doesn't really make any sense, right? Because there's no way that the shortest path from Chicago to LA goes through New York, right? So why are we visiting New York before we visit some more promising place like Denver? Okay, I'll admit, like, we're probably not going to go through Denver to get to LA, but at least it's better than New York, right? So let's maybe think about how we could solve this problem, all right? So to solve this problem, let's kind of go back and remember how we used to do things in Dijkstra's, all right? So let me just kind of first put down what I said right now. The intuition behind A star is that Dijkstra's visits vertices based on how close they are to the start, right? So this gives us a poor runtime, right? So one thing I want to emphasize before we kind of start talking about maybe solutions is Dijkstra's algorithm will work, okay? The problem with Dijkstra's is that the runtime of finding the shortest path from Chicago to LA will be really, really slow because we're unnecessarily visiting places like New York that wouldn't possibly be on the shortest path, right? So in order to think about this fix, let's first recall right? In Dijkstra's algorithm, the priority of a given vertex is, let's say, the closest recorded distance from start, right? So now what we're going to do is I want to change the priority of a vertex, right? So I want to change the priority of a vertex, right? So somehow I want to change the priority so that we prioritize going to Denver before we go to New York, right? That's my problem here. So what we could do is let's maybe have two terms in the priority of a given vertex, all right? So let's talk about A star right now. So in A star, we're going to have two terms that constitute the priority of a given vertex. All right, there's going to be two things that kind of come here. The first one is actually the exact same as Dijkstra's. We're going to continue keeping track of the closest recorded distance from the start. All right, that's the first thing. The second thing that we're going to do, and both of these added together will give us our priority. Let me kind of denote that quickly, that when I add these together, I get my priority, is that we're going to put a guess or heuristic, if you guys remember game trees, of how far the vertex is to the goal. And to maybe like help distinguish these, I'm going to kind of change this color. Let's make this green. Actually, no, I already used the color green. Let's make this brown. Yeah, the color brown probably wouldn't get used before. Okay, and let's make this. Let's make it this. Have I used red yet? No, I have not. Let's make it red. All right. Okay, so in A star, the only difference between Dijkstra's and A star is that the priority of a given vertex is the sum of two things. One of them was the same from Dijkstra's. The second is a guess of how far that vertex is to the goal. All right. So let's kind of come back here and look at our example so that we can understand what this means. All right. So if we're thinking about the first component here, the first component would be this brown line, right? Let me make that like a little thicker so we can all see. All right, so the first component here is this brown line, right? And the brown line is that it's the closest recorded distance from the start. All right, so if we only use this brown line as a metric, notice that, let's make it a little more pronounced. Notice that the brown line to New York is shorter than the brown line to Denver, so we'll go to New York first, right? Now what we're going to do in A star is we're going to add another term, which I like to call a guess or heuristic of how far the vertex is from the goal. So let's say this is my guess for LA, how far Denver is to LA, and let's say this is my guess of how far New York is from LA. So now what we'll kind of consider is that if we're considering New York, this is the shortest, this is like the priority of New York is the length of that pink highlighted region, right? That is the priority of New York. All right. So if we're considering the priority of, let's say, Denver, the priority of Denver is going to be this orange highlighted region, which is now shorter than New York, right? So what we're going to see here is that in A star, we're going to prioritize going to Denver before we prioritize going to New York, because this is Denver's priority, which is smaller than New York's priority, which is this kind of long pink highlighted region. All right. So kind of the next natural question to ask is, hey, Soham, like, how did you make this guess, right? Like, let's make it smaller. Might say, how do we come up with heuristics? So in this case, a possible heuristic we could use from going from Denver to LA is we could use the bird's eye distance. Since we know like the latitude and longitude of LA, so we could just say, hey, what's like the bird's eye distance from LA to Denver? So that's one metric we can use. And it turns out like for different graph problems, there's probably going to be different heuristics that we'll think of, right? So the last thing about heuristics, I won't really touch upon them in this video, is this idea of admissibility and consistency. Just to save time, I won't touch upon them in this video, but these kind of these terms kind of talk about whether a heuristic works or not, kind of roughly comes from understanding these two terms. So yeah, that's basically all of A star. The last thing to kind of note is the A star algorithm is the exact same as Dijkstra's algorithm. The only difference is that the priority of a vertex has now changed. And in A star, we terminate when we get to the goal, right? So those are the only two changes. Just to recap, the priority of a vertex is the sum of these two, and we terminate A star upon getting to the goal. So yeah, hope you guys enjoyed building the intuition for A star algorithm together, and I'll catch you in the next one.